Before we get started? Okay, so acids and bases. One of the reasons we look at acids and bases in living organisms is a lot of times the pH change of having more acid or more base is going to be what's going to turn something on or off in a system. So if we look when we split water, you've got one oxygen and two hydrogens. There's no way of splitting it equally. So what you're going to have to do is take and put the hydrogen, one of the hydrogens with the oxygen, the other one gets to go on its own. When it does, remember these represent there being two electrons shared between there for their bond. When it says, all right, we each brought an electron to this relationship, this set is more electronegative, it's bigger and stronger. It's going to say, you know what, you can leave if you want to, but you're not taking the electron. So what you end up with is the hydrogen ion left behind here that doesn't have an electron, but it still has its proton, so it's going to have a positive charge. This got an extra electron out of the deal, so it will have a negative charge in there. So you've got the hydrogen ion that is going to be more hydrogen ion is present. In acids, you're going to have more free hydroxide in bases. The hydrogen ion itself doesn't really hang out by itself. We write it out and refer to it as the hydrogen ion, but what it's actually going to do is jump onto another water, and you'll have hydronium. So you'll have 3 hydrogens on there instead of 2, but we don't really talk about it as that. We always just call it the H plus in there. That's H plus represents H3O plus by convention, and it's just the way it's done in there. When you look at the reaction of water splitting and coming apart, it's a reversible reaction. And we have this pH scale here that is going to represent where you are in that reversible reaction. So it goes 0 to 14. 7 in the middle is where you have these all together. Here is where you're going to have more free hydroxides. When you head on this side, it's more basic. Over here is more acidic, more free hydrogen ions in there. And depending on what is in the water to cause it to split up, it can go back and forth in the different directions across here. So the way we determine the pH is you can actually mathematically calculate it out. In pure water, you have one molecule in every 554 million of them that is dissociated. So if this is your substance, 1 in every 554 million of those has come apart to make these two things. It's not very much of it in there. If you look at that concentration in pure water, it's 10 to the negative 7 molarity at 25 degrees Celsius. So what the pH represents is the negative log of the exponent in there. So what you'll do is you take the negative times the negative of this negative 7 here, gives you a positive, and that's why it's a pH 7. So that's what it's representing in there. Both the hydroxide ion and the hydrogen ion are both very reactive and drastically affect other molecules, and that's why we care which one we have. So in this picture, you can kind of see that, on the far side here, you've got more acids available. You've got more hydroxides available in here. So this is the more acidic side. These are some examples of substances that are acidic, some examples of things that are basic in there. So pure water's here. Human blood is really close to that in there. A lot of times people get really upset at the idea of an acid and think it's dangerous, and it's not necessarily dangerous. It just needs to be in the right place. What they do is they have 2 different metals in the battery in there that are going to have different charges, and then there's water in the battery that allows that to do that, and it makes the water acidic because of, yeah. The battery itself, its makeup, creates the acid in there. So a lot of times battery acid is one of those things that people, as a little kid, you're told, don't touch the battery acid in there. If the battery's broken, don't touch it. And at some point you see a broken battery in something and you're like, well, I want this to work again. I got to take out the battery. You touch it and you go, I'm not going into flames or anything here. This battery acid stuff isn't all that bad. And it's not that it's good for your skin. You just don't want to leave it on there for a prolonged amount of time in there. However, lemons are really close to that, and nobody gets really upset if you touch a lemon in there. You drink this stuff. So the pH, it's about things being in the right place at the right time. Your stomach acid is about a pH 2, so it's very close to this. These things can be very corrosive. So if you put a lemon on the paint of your car, you'll damage it. Battery acid on the paint of your car, you'll damage it. Vomit on the paint of your car, you'll damage it in there. But it doesn't happen instantly. It happens over a little bit of time. There are some acids that are more reactive because it involves more electronegative things. So hydrofluoric acid, very reactive. That one would actually probably cause you some discomfort to run into it right away. Sulfuric acid is also one that's going to be really strong, potent, and reactive in there. And it just has to do with how strong this is pulling things away. But like hydrochloric acid, no, you don't want to put your hands in it, but it's not nearly as bad as some of the other ones are in there. So you've got this whole range in here. And because of it being logarithmic in there, what this means is a pH 5 is 10 times more acidic than a pH 6. A pH 4 is 10 times more acidic than a pH 5. 3, 10 times more than 4. So each whole number jump is actually a 10-fold change in there. So if you were to look at it, it would be more like a bell curve that scoops up at the end and then scoops back down at the other end. The lower the number, the more acidic, so it's going to be a higher concentration of hydrogen ion. Once you get on the other side of 7, the bigger the number, the higher concentration of hydroxide in there. It's kind of a weird thing that it comes out to be 0 to 14. 14's an odd number mathematically for things. But that's the way the scale works. So when you put the substance in water that's going to create it to be acidic in there, what you have is, so you put hydrochloric acid into water, you're going to have these separate, you're going to have free hydroxide, or free hydrogen ion and free chloride ion in there. For something that makes a base, sodium hydroxide, you end up with the sodium being free and the hydroxide being free in there. So when we talk about something being a strong acid or base, it means it's going to completely dissociate in water. We represent that using just a one-way arrow. If it's a weak acid or base, it's a reversible reaction in there, and it will come up with its own fixed ratio at equilibrium, but we indicate that with a reversible arrow in there. So your pH scale in any aqueous solution is always considered to be done under standard conditions of 25 degrees Celsius. So you look at the concentration. These brackets here represent concentration. You're looking at your concentration of the hydrogen, concentration of hydroxide, and between the two, the concentration is a constant at 10 to the negative 14th. Oops, excuse me. So in a neutral solution, in here, you've got hydrogen ion is 10 to the 7th. Excuse me. Allergy season is starting, so. The bad season started 2 days ago for me. Hydroxide here, that you're going to have 10 to the negative 7 in there. So when you multiply 10 to the negative 7 times 10 to the negative 7, you add these exponents in here, and that's how you get the 10 to the 14th. You're not going to have to do this math in here. This is here mostly to show you that, yes, there is a mathematical basis behind this. What you're going to want to know, 0 to 7, the acid range, 7 to 14, the basic range in there. This math is one of those things that you'll get to do this in chemistry and kind of beat it into your head at some point in there. The reason it's in here is I want you, when you see pH of things in here, to not go, well, that whole pH thing confuses me. You can look and go, pH, that's that acid-base stuff in there, and move on and understand the concept without going, I don't understand what pH means in there. That's the only reason we cover it like this. So the reason it switches to a positive number is your pH is the negative log of that, the log to the base 10. So if you haven't had the math for these kinds of things, don't worry about it. You do very few calculations in here of things. I'm not a big math person, so if there's a way I can leave the math out of it, I do. So with a buffer is a substance that's going to help to minimize the pH change in a solution. So if the pH change is going to turn things on and off, for example, one of the things it influences is when you inhale and when you exhale. So when you start to become too acidic, you need to exhale. When you need more to become more acidic, you're going to inhale in there. So that triggers the breathing. And you need to have that be pretty finely regulated, but you don't want it to be so finely regulated that you're having to do tiny little shallow breaths all the time. That's not real efficient. You need to be able to accelerate your activity level and still be okay and let the breathing slowly catch up with it. You can't function. If you had to just get up and go, okay, I'm going from sitting to standing here. I've got to slow this down so that I can build up my speed and adjust to it. In there, that wouldn't be effective. So that's why we want to have buffers, so that that isn't so overly sensitive in there that we can't function. And what a buffer will do is it's going to have a pH range that it will work. I think of it like a kitchen sponge. When the kitchen sponge is all dried out, crusty, sitting on the side, when you first put it under water, the water all runs off. You're not buffering any of the water flow into the sink. It's not in the buffering zone. However, when it starts to get soft again, then it can absorb some of the water that flows into the sink, and it's going to buffer how much ends up in the sink. Eventually, it's going to get saturated, and it will be past the buffering zone, and as much water as you pour in falls into the sink. So the buffer is just going to have a little range in there where it's going to take a little bit more work to push you outside of or change the pH of what you need. So any questions on pH? So other things where pH becomes important: acid precipitation, so rain, snow, fog, with a pH of less than 5.2 is considered to be acid precipitation. Burning fossil fuels releases sulfur oxide and nitrous oxides in there to create acid rain. A volcano is going to create acid rain, so there are natural things that create it in there. I took my high school class down to Seeley Lake on Monday, and they checked the pH of the lake, and it was about pH 5 in there. And that lake down there, it's not a lake that you would want to put your body in for various reasons, but that's probably a pretty good indicator of the rain that falls in this area and runoff that you get in this area, just because it's so close to the road. And I don't know that there's a spring that feeds it. It's pretty swampy. So carbon dioxide in the ocean, it will react with seawater to form carbonic acid and then dissociates to make bicarbonate and carbonate, and it will affect coral and other organisms. So coral is made up of it has a lot of calcium carbonate in there, and it will start to dissolve away the coral in there and break it down. One of the reasons it's significant is your coral and your bone have similar composition in there. So when you look at things, if it's affecting the coral, if you put that in, if you were to take that into your body, it's going to affect your bone as well. And it's not just from pollution that will affect the ocean with that. One of the ways they know what will happen if the pH of the ocean changes too much is if you look at places that are downstream of ocean vents that are volcanic vents. That's going to cause a huge pH change in there. So you can actually see if there's an underwater volcano that the coral downstream from it where the more acidic ocean floats by is going to damage that coral a lot more. So that is the section there on acids and bases. So you were supposed to go through the section on 4 on your own. Did anybody have any questions on this? It's okay to ask them if you have them. Somebody's got to break the ice and ask the first question. Couple things when you're looking at this. When you go to name carbon structures, naming them is actually fairly easy when they're small like this. You look at how many carbons are in there. If there's 1 carbon, the prefix is meth. If there's 2, eth, 3, prop, 4, bute. So if you had ethyl alcohol, how many carbons do you think are in it? 2. Methane. Methane, 1 carbon in there. Butane, 4. So the names tell you how many carbons in there. The ending, ANE, tells you that it's got single bonds. ENE tells you it's got double bonds. YNE tells you it's got triple bonds in there. So really easy to use with that, and you're going to want to know those. These are some examples in there. If it becomes round, a lot of times you'll call it cyclo something. Benzene is a common ring in there, but you can see that you've got butane here that's got 4, propane here, or isobutane. So in biology we like to give things more than one name, and chemistry is just as guilty. So it's also isobutane because it's got 4 carbons and it's in a different arrangement in there. It can be branching. The isomers are going to be the variation of the architecture. A structural isomer is going to differ in the arrangement of the atoms. Here they're arranged linearly. This is an isomer. You still have 5 carbons over here. 1 of them is off to the side. Your cis-trans isomers are going to involve having a double bond, and then you have 2 substances in there that can either be on the same side or on opposite sides. If they're on the same side, it's cis. If it's on opposite sides, it's trans. So the way I remember, trans is across, cis on the same side, kind of like sisters. Although I think with my sister, she thinks we're more trans. Just yeah, not a lot of friendliness with her. But if it helps you remember, your sister is supposed to be your friend on your side in there with that. So anybody think of something where you see this used in naming things? You'll see it in the grocery store. So they'll talk about things having trans fats in them. Trans fats means their arrangement is opposite like this. So when you have opposite arrangement, it's going to take a different enzyme to work on this than it is this. They'll have different properties. Then there's the enantiomers. This is the one that's sometimes a little hard for people to grasp. And the right and left hands is kind of the best way of doing it. With this, you've got a carbon, and you're going to have 4 different things around it. They are said to spin light in different directions. So I have no idea what was going through someone's head when they decided, hey, I've got this solution here, let's shine a light through it and see what happens, and I've got this other one and shine a light through it and see what happens. What led to that little escapade, I don't know. But in any case, if they're arranged differently, they will spin light differently. So you've got right and left isomers in a sense, except we call them L and D isomers. Anybody think of something you see that's got that? Because of all 4 are different, and so it actually has slightly different geometry in there. Light's going to want to take the easiest path, so one side's going to be easier to get around than the other. Can you think of something where you may see that? So all of your amino acids, you've got 4 different things around the carbon in there, and they'll be L and D isomers. Most of the time what you're going to see in living organisms is the L isomer. If you purchase amino acids, a lot of times you'll see L in front of it, so like L-tyrosine, L-glutamine in there, and that's what it means, is this is the isomer that you're buying in there. And that isomer in there can actually have a pretty profound effect. The drug thalidomide, it was one that was given for morning sickness some years ago, and they found it was causing birth defects in there. It's a teratogen, and it was causing very major birth defects. And it ended up that it was just one of these isomers that causes birth defects. One was not causing problems. So they could put it into the body, and what would happen is the liver would process it and make half of them this way, half of them that way. So even though they weren't giving the person the one that was causing problems, it would turn it into that in the body and cause the birth defects in there. So one had a beneficial or a helpful effect, the other one was causing major birth defects for people. So the drug was pulled off the market. It's been reintroduced back onto the market to be used for certain conditions. However, if you get put on thalidomide, it is also mandatory that you are on birth control in there, because they know it causes birth defects. So, and they don't usually just say you're going to be on the pill. They want something where they can have a little bit more control over it, where you usually have to be on some sort of implant or getting an injection in there for the birth control, so that they know you're not just forgetting to take it because of it being so damaging in there, or you've had vasectomy or something like that, or your significant others had a vasectomy. They aren't messing around. They don't want birth defects coming from it in there. So when you look at the carbon skeleton, there are different functional groups that can get attached to the carbons. And that's what all of these are, is those functional groups in there. You've got your chemical name here, your structure, the name of the compound. So your hydroxyl group in there, those tend to get put on things that you want to help dissolve the compound in there. So if you were looking to make an artificial substance in there and you wanted to be able to have it be water soluble, if you put hydroxyls on there, an alcohol group in there, you're more likely to be able to make it be water soluble. So you can put these functional groups on something when you create a chemical for the specific properties that they have. Your carbonyl group here, this is what's going to be in your aldose and ketose sugars in there. This is an acid group. An example would be on acetic acid, which is in vinegar. The amine group, this is what you're going to have on one side of an amino acid in there. It can be ionized with water. The sulfhydryl group in here, these sulfurs will form these double bonds in there that are very strong to give certain properties in there. So if you're going to create something that's going to have, you need a lot of strength in there, you may want to put some sulfhydryl groups on it. Phosphate, this will give a negative charge, can allow it to react with water. Methylated compounds, these don't necessarily react a whole lot, but they are used a lot in the body to turn genes on and off. And turning genes on and off can help turn on the function of sex organs and turn it off. There. So that's just kind of an overview of those. So let's go ahead and have you go through your notes, and I'm going to give you some things to focus on for your first test.